Now, have you ever wondered why a spring system like this one is very difficult to stretch when all the springs are attached, as opposed to when just a few of them are attached? In this lecture, we are going to investigate the arrangement of springs, and we are going to understand how the chest expander works. Hello and welcome to this video where we are going to investigate the stretching of spring under the action of forces, especially where we get several springs and then we arrange them in a particular pattern, either in series, parallel, or a combination of those patterns. But first of all, we are going to start with a single spring over here and then look at its properties. So we are going to determine its length and then apply a force to it. Of course, it's going to stretch, measure the extension, and then from the force and the extension, we are going to calculate the spring constant. And this is what we are going to have. So first of all, I'm going to put a meter rule just next to it so that we can be able to measure its original length, which will help us to determine the extension when there is a force applied to it. So that is one of the methods that we can be able to determine the extension. So when we have that particular spring, you will be able to see that the first turn is put against the 2 centimeter mark, while the last turn is just next to the 5.2 centimeter mark. That tells you that the length of this spring is 5.2 minus 2, you get 3.2 centimeters. Now to this spring, we are going to suspend a weight here, a 200-gram weight or mass. And then we are going to realize that the force which is exerted on that spring will be equal to the weight of that mass. So I'm going to have another spring just next to it so that we can retain the previous position of that spring. So remember, this spring is exactly equal to this one, but onto this one, we are going to suspend this 200-gram mass. And you can see, as soon as we do that, its length becomes longer. But remember, this point does not change. So how do we get this extension? There are two methods that we can use here. The first method is where we get the initial length of the spring, which we know is 3.2. Then we get the new length after we suspend that mass and then find the difference. The other method is to get this scale reading. This one can act as a pointer. We get the scale reading when there is no mass on it, and then get the scale reading when there is a mass, and then find the difference between those two scale readings. They'll give us the extension of the spring. So let us quickly use those two methods in order to determine the extension of that spring. So over here, we have been able to see that the length of this spring, when there is no load on it, or the original length is 3.2 centimeters. And we did that by doing 5.2 minus 2 centimeters, 3.2. Now let's get this length when there is a mass on it. We are going to do 6.2 minus 2. Again, that one is going to give us 4.2 centimeters. 4.2 centimeters. And we can be able to determine this extension here. The extension of a spring is the change in the length of the spring when a force is applied onto it. And it will be equal to the final length minus the initial length. And these values are very simple to get the difference. 4.2 minus 3.2, and I get 1 centimeter, 1.0 centimeters. This is equivalent to 0.01 meters. There is a reason I want to express it in meters, because I'll use that extension in meters to calculate the spring constant. Now let's look at the second method of working out the same extension. This extension here. This extension is given by this pointer reading or the scale reading, which is 6.2 minus 5.2. And again we get 1.0 centimeters. So two very simple methods of determining the extension of the spring. And at this point, let's quickly calculate the spring constant K. For us to be able to calculate the spring constant, we are going to divide the force that the spring is supporting by the extension. We have suspended a 200-gram mass. This 200-gram mass has a weight, which is the force. Weight is equal to mg. The mass of this particular object is 0.2 kilograms. I want to use the value of g as 10 Newton per kilogram. And you can be able to see that the weight of that mass is 2 newtons. Another way of getting this weight is simply by recalling this, that 100 grams on Earth has a weight of 1 newton. How about twice that mass? Definitely it will just be 2 newtons. So the force is this much, which is 2 newtons. The extension is 0.01 meters, and that is what gives us 200 newtons per meter. What does this mean? This is what it means, that a force of 200 newtons is required to produce an extension of 1 meter in that spring. That is what it means. Now, we are going to get several of these springs, which are similar to this one. They will be similar because they will be having the same spring constant and probably the same length, but I might change the length of the spring so that everything fits within this particular space, because I wanted the diagrams to be big enough for you to be able to see, as well as to produce the necessary extensions when I apply a force of 200 grams. So let's quickly look at a situation whereby we have connected these springs in a given pattern. And the first connection is where we have the springs connected in series, in parallel, and then I'll connect them in series, and then I'll have a combination of all those of parallel and series. So first of all, I have all of them connected like that. Let's look at the situation. The situation is that I have this spring, but this time the length of this spring is different. Look at it from here. You can see that its length is actually 2.4 centimeters. It's not 3.2. I did that so that extensions like this can fit within, systems like this can fit within the space which we have here. But the spring constant remains the same, 200 newtons per meter, and that when we apply a force of 200 grams on a single spring, the extension still remains 1 centimeter. So it's only the original length of the spring that I have changed. Everything else remains the same. So, okay, first of all, let's remove that meter rule so that we can create more space. So to each one of these systems, I'm going to suspend the 200 gram mass. We are going to have a mass here, a mass here, a mass here, and a mass here. And you will agree with me, as soon as we apply those masses, the system, the springs are going to stretch. For instance, this is what now we have. We can see that we have applied a force of 2 newtons on this spring and the extension becomes 1 centimeter. Its length has changed from 2.4 to 3.4. an extension of 1 centimeter. And the spring constant will be 2 newtons divided by 0.01, and the spring constant here is still 200 newtons per meter. So over here, we have already been able to see that the spring constant for this first system, K, is 200 Newton per meter. What will be the spring constant for this system here? For me to determine the spring constant for this system, I need to get the total extension of the system. So first of all, let's look at the force that I have applied on that system. The force remains the same. It's 2 newtons. This 2 newtons is supported by 2 springs. It's like 2 people who are carrying the same log, or maybe they are carrying the same ladder, and at the center of the ladder there is a huge weight. They are going to share that weight. Each one of them will apply half the weight of that particular weight that they are supporting using the ladder. In other words, this is 2 newtons. This spring is going to support just 1 newton. This other one will support the rest, 1 newton. Now let's go back here and ask ourselves, how much force was this? 2 newtons. How much extension did it produce? 1 centimeter. So we argue out like this. If 2 newtons produces an extension of 1 centimeter, 1 newton will produce an extension from here to here, or from here to here, of 0.5, of half 1 centimeter. So the extension which is produced in this spring, or this spring, is 0.5 centimeters. And again, you can use these readings here to tell that it is 0.5. Because over here I've got 2.4, here I've got 2.9, 2.4 minus 2.9 minus 2.4, you get 0.5. So that will be the extension of this spring. The same extension will be here. So what will be the total extension of this system? It is not 1 centimeter. It is still equal to the extension of one of them. This is the trick here. If you have springs in parallel and a force is applied, the total extension of that system will be equal to the extension of just one of the springs. So let's see how we can work out the value of the spring constant when we've got 2 of them in parallel. It will be equal to the force which they are supporting, which is 2 newtons, divided by the total extension there, which is 0.005 meters, and this will give us 400 newtons per meter. Again, what does this mean? That we require a force of 400 newtons to produce an extension of 1 meter in that system. You can see the system has become stiffer. It is now more difficult to stretch that system. And this is how springs are arranged in the exercise machine, which we call a chest expander. When the springs are arranged in parallel, the system really becomes difficult to stretch. Why? Is because the spring constant has gone up. So long as we know the meaning of the spring constant, we never go wrong. Over here, we just need a force of 200 newtons to produce an extension of 1 meter. Here we need double that force. So it's as if K2 is equal to twice K. 2 times 200, you get 400 newtons per meter. So we can draw a conclusion here. If we have 3 springs, then the value of the spring constant will be 3 times 200, which will be 600 newtons per meter. And it's again easier to see that, because if there were 3 springs, each one of them will support a force of 2 divided by 3. And then we are going to calculate the amount of extension we have there. And by following the same method, we can be able to show that the spring constant will be equal to 3K, where K is a spring constant of one of the springs. Now let's quickly look at a situation where we have springs in series. So unlike springs in parallel where the two springs share this weight, these two springs, each one of them will support these 2 newtons all by itself. This is 2 newtons. So this will support 2 newtons. So its extension will be from here up to here, which is 1 centimeter. The extension for this one will be from here up to here, which again will be 1 centimeter. So the extension of this spring, the extension of this spring, and the extension of the first spring, they are the same. 1 centimeter, 1 centimeter. What will be the total extension? The total extension will be 1 plus 1, which is 2 centimeters, and 2 centimeters is same as 0.02 meters. Let's look at the spring constant here. The spring constant will be the force, which is 2 newtons, divided by an extension of 0.02 meters, and this will give us 100 Newton per meter. So the system becomes much easier to stretch, because to produce an extension of 1 meter, you just need a force of 100 newtons as compared to the force you require here to produce the same extension. Remember the meaning of spring constant. You need a force of 200 newtons to produce an extension of 1 meter in that spring. Over here, you need 200 newtons to produce an extension of 1 meter in that system. Over here, you just need 100 newtons to produce an extension of 1 meter. So this one is more easier to stretch than this one. And in fact, this one is easier to stretch than this one, and this one is easier to stretch than this one. So this one is the stiffest of them all. At this point, there is something which I'd like you to understand. In fact, 2 things. That if we connect 2 springs in series, the value of the spring constant will be equal to half the spring constant of one of the springs. Like that. Because we can be able to show that if there are 3, then it will be K divided by 3. If there are 4, it will be K divided by 4. And then the next thing which I want you to realize is this. Given 2 springs, they have the same diameter made out of the same material, the same wire of the same diameter. But one spring has got twice the length of the other one. The longer one will have a spring constant which is half the shorter one. So when you look at 2 springs and one of them is longer and another one is shorter, just know that the longer one has got a smaller value of spring constant compared to the shorter one. That is how you can tell. And if the length is double, then the spring constant here will be half the spring constant there. So those 2 points are very, very important. Now let's look at a combination of this and that. In other words, the first 2 springs are in parallel, and then to that parallel system, another spring is connected so that it is in series with a parallel system. We want to, first of all, determine the total extension, because our aim here is to determine the value of K. So I want the extension over here, which will be 0.5 centimeters. Remember, this 200 grams is shared between this spring and this spring. This one will support 100 grams, in which case its extension will be 0.5 centimeters, because we know 200 grams produces an extension of 1 centimeter. So 100 grams will produce half of that extension. But this other one here supports the 2 newtons all by itself. So remember, this is still 2 newtons. This one supports the 2 newtons all by itself. So the extension here is still 1 centimeter. What will be the total extension? The total extension will be 1 plus 0.5. Or rather 0.5 plus 1, and we get 1.5 centimeters. And this, of course, is 0.015 meters. What will be the value of K? The value of K will be equal to the force divided by the extension, or divided by the extension. Let me use E. And that will be 2 newtons divided by 0.015 meters. And this one will be like 2,000. If I multiply up there by 1,000 divided by 15 meters. The value of K, if I divide by 5 here, I'm going to get 400. If I divide by 5 here, I'm going to get 3 meters. And this one will be like, if I factor out 200, just interested in getting this 200 out because it's the value of K. Remember, this is the K total, so that we can distinguish it from this K. So this K total is going to be equal to, I factor out 200, I remain with the 2 inside there, and I have 2/3 Newton per meter. And you can see that system, the value of K for that system can also be calculated in terms of K. And this one will be 2/3 K. And that is how you would work out the spring constant when you're given several springs arranged in a particular pattern. For more information on how we deal with this kind of calculations and other calculations in other topics, in fact, in about 10 topics, I have good news for you. I have designed a course called Master O-Level Physics Part 2, where I take you through 10 topics. This is just one of them, which is referred to as Hooke's Law. So below this video, just click on that link. It will take you to the course directly. And when you get to that course, there are several video lectures that I've given you so that you can make a decision as to whether or not to purchase the course. But I can guarantee you, the first time you go through those lectures, you will not turn back because you will want to know what happens in other topics. So I take this opportunity to invite you to go to that link and learn more physics, even if you will not have decided to purchase the course yet.